All right, so everything else we're feeling okay about? And you can see we've done a number of these differential equations, and I'm trying to mix it up and let different integral processes show up in there. And it's not like you're going to get to one and go, oh crap, there's some long division I have to do. That's not going to show up. You know, the ones we had to do long division before you even got started. So there are some things that may not show up, but again, I'm trying to show you as much as possible through the homework, through the quizzes, through the examples, so you'll be ready on test day and you won't go, oh man, that's dirty. But if you're not looking at all those problems, you're not exposing yourself or reminding yourself about everything. So definitely do this work. And at the very minimum, I realize that at some point it's just algebra, but some of you gotta have holes in your algebra that you need to kind of iron out and figure out. So do what it takes. I try to teach you, especially second semester like you were in college, and let you be empowered in your own way. But I want to really encourage you to kind of stay in there and try to do as much as you can. It's a very doable test, but there's going to be a lot of different topics on this test. We're starting a new one today, which is not really that new. It's very much like a differential equation, and it is a differential equation. But we're also going to be working on slope fields and all kinds of different things that will impact this test. So anyway, we're going to jump to Newton's law of cooling. You may know of Isaac Newton as one of the founders of calculus, but he also did a number of other things. And one of the things he did was talk about cooling. And this kind of makes sense. You know how when you're dealing with exponential growth or decay, and usually decays, like if you're talking about carbon-14 dating, it's decaying, but it's approaching what? Zero, right? The limit of that eventually is going to be approaching zero. But if I took a hot cup of coffee and put it on a counter, it's not going to, the temperature is not going to approach zero. It's going to approach what?
Room temperature.
Room temperature, right? And if I took a hot cup of coffee to hell, it's going to actually increase in temperature to whatever the temperature of hell is or whatever. So it's either going to grow to a temperature or decline to a temperature. It just depends on the temperature of the room. And Newton said that. He said, Newton's this was his postulate or his law, which holds up. And if I had planned better and had more time, I used to take, and if I had my hot coffee pot, I used to heat up boiling coffee and take one of Reeves' and then just pour it on my head. No, I used to take it and actually run this experiment through the course of class. So I would actually heat it up. We would take an initial measurement, right? And then I would seal up the container so air wouldn't affect it or whatever. And then we would teach class for 30 minutes or so. And then we would use our guesstimate based on our room temperature. It was really probably a good experiment I should do, but I just got behind. So, and then we'd say, all right, guys, let's do the math. And we've kind of projected how long it's going to take us to actually do the problem. And we figured in the time interval. And we said, all right, what temperature should we end up with based on this model, based on the temperature? We'd figure it out. And then we'd get out and pull out the thing. And I mean, we were accurate always to within a degree, which is pretty great, because considering it started at 212 degrees boiling and it came down over the course of 30 minutes. So it is an accurate formula that he came up with, or differential equation he came up with, but here is his differential equation. He said that the rate of change in the temperature of an object, what does that sound like? So the rate of change, dt, the temperature of an object, I tell you what, why don't we just say let y to avoid multiple variables, and you'll see why in a second. So dy dt, where y would be the actual object's temperature, okay? So the rate of change in the temperature of an object is proportional, which means what? Times, because that would mean directly proportional. So k times, but he said not proportional to the actual temperature, he said proportional to the difference between the temperature of the object, which would be what? The y, and the temperature of the surrounding room, which would be some other variable, and we're going to let the room temperature be big T. So if I let big T be the room temperature, then the difference between the temperature of the object and the temperature of the room would be y minus T. Y'all seeing that? And that right there is Newton's law of cooling as a differential equation. But I would want to solve that, right? So the process of solving that and getting a workable equation where I could just plug in time and I could figure out how much the temperature had changed, or I could plug in a temperature and figure out how much time it changed. That part I would have to solve. And that's where the differential equation comes in. And I think I've done that, yeah, I did that for you right here. So if you take that differential equation right here, now we already know that dy dt equals ky gave me this, right? Whenever I have a dy and a y and just a direct proportion, I could just jump to this step. Well, I'm hoping you can jump to Newton's law of cooling result as well. And Newton's law of cooling does show up, but if it's ever a free response question, show all your work. If it's multiple choice, jump there and just use it. Really becomes an algebra problem. But this definitely does not look like that. It resembles a little bit, but it's different. So let's do the math on it. So separating the variables, multiply by dt, moves that over there. Divide by y minus t, moves it over here. That should give you this equals that, right? Integrate both sides, and when I integrate both sides, and by the way, you're going to know big T. Big T would be the room temperature. So you'll have that. You won't even be annoyed by that variable because it'll be like 67 degrees you would put in there. Okay? So to integrate that, that's not a rule, but I could easily do a U substitution. So if I let U equal y minus the room temperature, then du equals dy, right? Because the big T is a constant, it would go away. So that's my u, that's my du. So technically right here, I have the integral of 1 over u du, and when I integrate that, I get natural log of the absolute value of u. Integrate that, and I get kt plus c. I e both sides, the e and the ln cancel. Drop that down, swing the c out to the front. I would never even take this step. I would just swing that out to the front and get to here. What does the c do with the absolute value? Absorbs the plus and minus. So absolute value kind of just vanishes there. And then I add t to the other side. So what's the main difference between this and dy dt equals ky, dy dt equals ky minus t? This goes to that, whereas this goes to that. So it really looks like the same formula, except this difference minus t ends up being a plus t on the other side. So if you're doing a Newton's law of cooling formula, if you know that, the only difference is an exponential function, because it has a shift of 0, right? It's approaching 0. That's different. Now we have an exponential function. Isn't that t basically like your horizontal shift? Right? It's like I'm shifting up to t, and I'm going to be approaching that room temperature, whatever that is, not the x-axis anymore. So that's really the only difference between Newton's law of cooling and the exponential stuff that we've done. And you just have to remember this. If I were to give you an initial temperature, an initial amount, right? You know how normally, if I say, oh, we started with, blah, and you always use that for your C value? That's not going to be the case here. Because look, if I have, just be careful about this. All right, let's just say my room temperature is 67 degrees. So you start with this equation. What if I tell you, hey, at time 0, the temperature of your object, say your cup of coffee, is 200 degrees. A lot of people have gotten in the habit of going, oh, that's your C value, right? Because it's your initial amount. And they've been just taking this, and because most of the time I don't have that 67 there, do I? When I've been dealing with exponential growth, you plug a 0 in there, all that goes away, and your C equals 200. But now that I've got this T in there, be careful, because if I plug a 0 there, and I plug a 200 here, yes, that goes away and gives me a 1, but my C is not 200, is it? It ends up being 133. So be careful and don't just kind of get into your head that the initial amount is always C, because it is not when you're dealing with Newton's law of cooling, just because of the algebra. All right? So let's just do some of these. Check out some Newton's law. And I think you're going to be in pretty good shape. So I have one just done for you right now, but here's an example of what it would look like. Let Y represent the temperature of an object in a room. That could be a cup of coffee. It could be a human body. I know when you watch like CSI Miami, and they're like, oh yes, the cause of death is blah, 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 but the time of death, and they just know, yes, it looks like he died 8 hours earlier. Those guys, they might have every chart memorized, but my guess is they've got a little table, right? And they know that the human body is typically what, unless you're under duress? 98.6. So they know the object, and then if it's 75 degrees out, that's kind of the room temp, right? So if they've been deceased for a while, that temperature of the body is going to approach whatever that room temperature is. And they can tell by the temperature of the body how long it's been because of Newton's law of cooling. Unless the temperature of the body is 75 degrees, in which case he's already pretty much hit that flat line of that exponential curve, and then there have to be other factors, sadly, which we don't need to get into, that you would explore. But anyway, based on this model right here, it says the temperature of the object in the room, which temperature is kept at a constant of 60 degrees Fahrenheit. The object cools from 100 to 90 in 10 minutes. So what am I giving you here? It says the object cools, right, from 100 to 90 in 10 minutes. How much longer will it take for its temperature to decrease to 80? So what am I giving you here? That the initial temperature is 100. And so the initial temperature times 0, 100, and then what? Time 10 is 90. Right? Now, technically, what I'm trying to look for is not the time it takes to get to 80. AP does this, and it's annoying, but they do it. So I'm just kind of prepping you for it. This question did not say, hey, if the initial temperature is 100, and then after 10 minutes it's 90, it didn't say how many minutes does it take to get to 80. It said how much longer. But to do that, I'm going to solve for how long it took to get to 80. And then what? Subtract off that 10 minutes. Does that make sense? So there is a difference in that question. Be careful about that. On my test, if you miss that, you probably miss 1 point out of the 6. So it's not devastating. But on a multiple choice question on the AP test, they're dirty that way. And it just doesn't make any sense why they would do that and trick you up because you know the math. And of course, both answers will be there in the multiple choice waiting for you. But just be careful to make sure you're reading correctly. When I take the AP test at the end of the year, like the new ones that they put out, which I'm always kind of eager about to see if I can make a perfect score, I still have not. Almost every time when I miss something, it's because I just didn't read. I mean, occasionally I'll see something, I'm like, what in the world? And I won't know what they're even talking about. And usually when I look at the key, I'm like, ugh. But most of the time when I miss something, I'm very confident I'm right. And when I go back and I read it, I go, ugh, I just didn't read it. Okay, so be careful about that. So anyway, let's work through this problem. I don't even have to. I know that I'm cooling. This is clearly, to me, a Newton's law of cooling problem. I could use the differential equation, and that's fine. But every time I use it, it's going to be the same math. And what am I going to end up with? That. So I'm just going to jump straight to that, knowing that I have a cooling problem. And I'm just going to go ahead and plug my room temperature right in there for big T, and then I'm going to begin. And at this point, it really is not a calculus problem, is it? It's really more of an algebra problem. So brush up on your algebra. If you know who you are. If you struggle with solving systems or solving equations with multivariables, get some practice on these. Don't just hope it's going to work out. So I'm going to plug 0 and 100 in. I'm going to plug 0 in there and 100 in there. I don't get C as 100. I get C as 40. So the 40 goes back in there for C, right? So now that the 40 is in there for C, I use my next point. T is 10 and Y is 90. T is 10, Y is 90. Now I've got a little bit more math to do. AP they want to see this. They want to see that you plugged in 10, 90. But they don't care about any of this math. So just take your calculator out and go, all right, 90 minus 60, and you're going to see a 30 on your screen. And then go 30 divided by 40, and you're going to see a 0.75 on your screen. Then say natural log both sides, and you're going to see some ugly decimal on your screen. And then divided by 10, and you're going to see that. That's all they need to see. That's all I need to see. Okay? And if you left it as a whole number, that's fine. But if you have a calculator, man, use your calculator. And then now that I know C and I know K, I'm going to put the C in there and the K in there and answer the final question. And the final question was, how long does it take for the temperature to finally get to 80? So I'm going to put an 80 in there, and I'm going to solve for T. And again, They want to see that you plug that in there, but all of this, they're really not interested in. They might be interested in that, all right? But all of that is going to be in your calculator. So 80 minus the 60 is a 20. 20 divided by the 40 is a 0.5. Natural log the 0.5 and you get an ugly decimal. Divide by the ugly k value and you get the 24. And remember, the question wasn't how long it takes, it said how much more time, right? Or how much longer. So how much longer did it take? 14.094. Are you with me? Does that feel a lot different?
No.
Okay, it shouldn't, unless you haven't done any of the other work, and then it still feels a little new. But the more you're doing these, the better off you're going to be. So let's check a couple of these out. So here we're going to jump right into CSI. It says a detective finds a murder victim at 9 a.m. The temperature of the body is measured at 90.3 degrees Fahrenheit. 1 hour later, the temperature of the body is 89.0 degrees Fahrenheit. The temperature of the room has been maintained at a constant 68. Assuming the temperature of the body obeys Newton's law of cooling, write a differential equation for T. Now, what did I ask for, an equation or a differential equation? So if you right now wrote, oh, y equals CEKT plus big T, or plus, I guess, 68, you would miss this. That's not the differential equation. What's the differential equation? The rate of change of the temperature. Now, that would be big T here, okay? So they're trying to mess with you. The rate of change of the temperature of the body, that's the big T here, over little t, is proportional to what? The difference in the temperature of the body and the room, 68. Now you can see they're using big T differently than that standard equation, aren't they? They're letting big T be the y, and they're letting a former big T just be 68. Are y'all seeing the difference? But they're dictating this problem by making you use their variables. Are you seeing that? Yes, no? Now, if they didn't say that, if they just said, hey, assuming the temperature of the body is y, then you'd have dy dt equals k y minus 68. That would be more in the form that I used. Anybody have a question with that? Okay, so if you have this, what's the next step? So what are you doing?
Moving things over.
Okay, now do I have to actually do that? It says solve, well, it says solve it, I'm going to solve it. But if it just said find the equation, I could jump straight to what? Not y. I would jump straight to t equals ce to the kt plus 68. But if it says solve the differential equation, then we need to see that solution. Okay? So I'm going to talk to him.
Move things over.
Slide that down. Slide that up. Integrate. Natural log. I can do a u substitution. When I'm done, I'll have natural log of this equals k little t plus c. E both sides gives me this. E to that. But I know that e to that c ends up being out front. Last step would be what? Put the plus or minus, which this big C eats, and add the 68, and I'm right here. And that would be pretty adequate for showing your steps for part A. This would be part A. No, sorry, this would be part B. Differential equation, solve the equation. Now, we got to be a little bit better than this because we still have K and a C in there. So at this point, we've got our general solution, but they want to solve that differential equation and then to estimate the time the murder occurred. So from this right here, where would I start? Now here's where people get messed up. Where people get messed up here is they go, well, the initial time, let's make that the time of death 0. Well, the problem with making the time of death 0 is that what would this be? I don't know. So I don't know how much has passed from the time of death to the time they actually found this murder victim. So what I'm going to do is make this my time 0. Are you with me? And then when I find the time that it was 98.6, maybe it's a negative number and I can subtract and go back to that time. Is that making sense?
Yeah.
So use what you know to be your time 0. So if I say, okay, right here at time 0, then I know that that's going to be 90.3. The big T is 90.3. I know that 1 hour later, at time 1, the big T is going to be 89. And basically, I want to know when the time was 98.6. I'm sorry, when the temperature was 98.6. That's the T I don't know. Okay? And if this is my 9 a.m., right? And then this is 1 hour later at 10 a.m., when I figure out what that is, which is going to be a negative time, I can subtract it from the 9 a.m. and get there. It's not the only way to do it. I'm just throwing something out. So what's going to happen when I plug a 0 in here and a 90.3 in there? That's right. So if I plug a 90.3 here, 0 there, all that goes away, and 90.3 minus 68 gives me what? 21.7? So my big C is 21.7, and now I'm kind of running out of room here, but I get this equation. Oh gosh, struggle. You're correct. Yeah, I was thinking 68.3 and 9. Sorry. All right, now what?
Plug it in.
Okay, so the other point is at time 1. So at time 1, which is not going to do much here, and you can listen, you can do minutes here if you wanted to, but I'm just going to do hours. But if you did minutes, then you would say what here?
60.
Times 60. But I'm just going to do hours. But usually if you read the question, it'll say, how many hours earlier was so-and-so, or how many minutes earlier, and then you let those units kind of drive your problem. Since I'm going to let that be 0, I can make that 1, or I can make that 60, but if you make it 60, you're going to be subtracting minutes from that. Okay? So right here, I'm going to plug a 1 in there, and that temperature was 89. So now what happens? And again, do this on your calculator. Make sure you're comfortable. So what am I going to do first? Subtract the 68 gives me 21. Then what are you going to do? Divide by 22.3. That gives you an ugly decimal. Then what do you, and that decimal, just to kind of help you see it, that gets you to here. Then what are you going to do? Natural log both sides. And again, you don't have to show all of this. If you can follow along with it in your calculator, you natural log both sides to get rid of that E. What?
You have a negative, but if you subtract 68 from 89,
What did I do? 89 minus 66 is 21. I don't know what I did. Oh, I did 22 minus 3. I have no idea what happened. I'm typing it in my calculator. So 21 divided by 22.3, not 22 minus 3. Or negative 3. 0.9417, and then you natural log it. Negative 0.06, right? And then if I had a value with the K, a number there, which often you do because it's not a 1, I would divide by that. So in this case, my K value ends up being negative 0.06006, yada, 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 but keep it exact as you possibly can. Okay, that's good. And then once you have that, I have this equation, T equals 22.3 E to the e to the negative 0.060 T plus 68. Don't forget the 68. So often on the test, people are so used to the exponential stuff, they forget the 68. So now that I have that, it says what? Or what would I do?
Estimate the time.
Estimate the time. So I would assuming this person's healthy, was healthy before he died, you'd assume 98.6, or if you knew other information, you would do that, but in the absence of that information, I would just assume 98.6. So again, I'm showing the reader that I know what I'm doing. I'm showing them, I'm plugging that in, but then at this point, all you have to do is solve it. So 98.6, I'm subtracting 68, I'm dividing by a 22.3, I am natural logging to get rid of the E, and then I am dividing again by and I'm going to go up there and grab that value. I'm going to divide again by the negative 0.06, and that gives me negative 5.265. So after all the algebra there, T equals negative 5.268 hours. Yes?
On the AP test, would it ever assume that we know something like the average temperature of a person?
Probably not. Yeah, probably not. This is a good question. So they probably tell you that, or the initial temperature or whatever, but that's a good point. They probably would not have you assume that. So at this point, you know that if I began this process at 9, 5 hours earlier, takes me to about 3 something, right? So it might be pretty obvious from your answers. They usually don't make you mess a whole lot with all this conversion. But if I really had to know the minutes, how would I find the minutes there? All of it by 60? I would take the decimal and multiply that by 60 to find the minutes. So I'm basically going to add 5 to that number to get just the decimal. Okay, and then I'm going to take that 0.26, multiply by 60, that gives me 16 minutes. So basically this means 5 hours and roughly 16 minutes, 5 hours and minutes earlier. So if I needed to, I could take that 9 o'clock, subtract 5:16. Of course, I can borrow 1 hour, which is what? 60 minutes. So that gives me 44. So at roughly 3:44 a.m., this guy was murdered. All right? Now, I seriously doubt the CSI guy comes in there and goes, hey, you got a pencil and paper? I need to crunch some calculus. Come over your TI Inspire. I doubt that happens. What he probably has is just a chart, right? Or some little app on his phone that he uses, and he's like, room temperature, temperature of the body, boom, and it spits out. So it's probably not a big deal anymore, but there was math behind that app, and the math behind that app was mixed up. All right? Now, you're going to know this more and more as you move through calculus, you move through this year. AP likes to test algebra some, but they really like to test understanding of graphs and charts and tables. So this was a problem. I want to say it was either exactly an AP problem that I just borrowed, or it was something similar that I just referenced. But here's a great example of an AP question. It said the graphs, probably tweaked a little bit, but it says the graphs in these figures below represent the temperature in Celsius of 4 eggs as a function of time. Okay? And it says measured in minutes. Match the 3 graphs with the descriptions below. Write a similar description for the unaccounted for graph, including an interpretation of any intercepts and asymptotes. So when you look at this is an egg, and you have a time axis and you have a temperature axis. Okay? So what would you say describing this if the axis starts right there at time 0, temperature 0, and this is in Celsius?
It's at 0, 0.
So it's at 0, 0. What does that mean to you?
It means that the answer can't be the second graph. Or wait, no. We're matching. Yeah, no,
What does it sound like it's doing? Okay, so I'm going to pretty near frozen, right? 0 degrees Celsius is pretty near frozen, which is, if you measure refrigerators keep the temperature pretty cold, but they don't want to freeze it. So 36, 38, 34, you want the colder it is, the longer your produce and your ham and all that stuff's going to last, right? So you're pretty near freezing, and as you move through time, what's happening? It's approaching 100 degrees Celsius, which is what? Boiling. So what does that sound like here? An egg is taken out of the refrigerator just above zero and put into boiling water? That sounds a lot like it. Now, so I would say that one really looks like A, but let's be a little careful. What about B? B says 20 minutes after the egg in part A is taken out of the fridge and put into boiling water, the same thing is done with another egg. That to me looks like this. 20 minutes later, so time has passed, then I still took it out of the fridge at a very low temp, threw it into boiling water. What does Newton's law of cooling do, or heating? It approaches the temperature of the room, and the room would be like the boiling water, right? Now, when you really get into it, and I struggled with this when I did my first experiment with that temperature gauge, is sometimes you have room temperature within a room temperature. Like if you think about it, if I were to be placing something into hot water, boiling water, right, that boiling water could be affected by an external temperature as well. So I was actually taking the temperature probe in a cup of coffee, but what was happening is the coffee was changing, the hot coffee was changing abnormally because of the temperature of the room. So there was the temperature of the coffee, which is kind of like a room temperature, and the temperature of the room. So really, what was the object? Was the object the water? Was the object the probe? There were so many factors going on that it messed up my experiment. And then the last time I did the experiment, we were on the money because I took a Yeti or something like that. Maybe it was one of those that have, what are the ones with the great lids that, not Yetis, but whatever. Some other brand. And it had Hydro Flask. I have a great Hydro Flask. It had a little small opening in the top. I put the probe right down there through the middle, the temperature probe through the middle, and sealed it up. So I really incubated it, didn't let it be affected by outside temperatures, and that's when my results were almost perfect. But anyway, so there might have been some other outside factors that are going on here, but we're doing the best we can. C, an egg is taken out of the refrigerator at the same time as the egg in part A and left left to sit on the table. Well, if I take it out of the refrigerator at the same time as A, that's at time zero. It's not going to approach boiling, right, sitting on the table. It's going to approach room temperature. I don't know what room temperature is, but I'm guessing it might be 20 degrees, right? So does that sound like this or this? 3. And then D said, well, the one I haven't accounted for is this. How would you describe this?
20 minutes after the egg in part A is taken out.
That's right. 20 minutes later, or after this one was taken out,
After the egg in part A.
I did what?
You took it out.
Took it out, put it on the table. You follow me? So you're probably not going to have a problem like this where you are actually writing that statement out, but it's very likely to have a multiple choice question that tests that kind of information. All right, check out this. It says a yam is put in a 200 Celsius degree oven and heats up according to that differential equation, where K is a positive number. So really they're just messing with you here, trying to get you, if K, normally my K value is negative, and K value is negative, it's a growth constant, right? That's what we've been saying K is. It's an exponential growth constant. Well, when exponential growth is positive, it does this way. So if you are cooling, your K value is normally negative, right? Well, they put the negative in there so that your K can be positive and the net result is a negative positive number, so it ends up being a negative number. So don't let that bother you. They're really just trying to force your hand a little bit and make you do the differential equation. So, if the yam is 20 when it's put in the oven, solve that differential equation. So how do I solve that differential equation?
You just do T equals C to the KT plus 200.
Can I?
Maybe, perhaps.
Because that's what I would do if that negative wasn't there. And again, if you do enough of these, you notice patterns, you're going to see this one when we get done with it. But if it's anything different, I wouldn't make any rash assumptions. So if it's me, it doesn't take that long to do a differential equation. I'm going to slide the dt up. I'm going to divide by the h minus 200. I'm going to integrate both sides. When you integrate that, a simple u substitution doesn't really change much, or anything except that u. You don't have to do any other adjustments. You'd see that when you do it. Integrate that, negative kt plus c. So when I e both sides, it's pretty easy to see that not a lot changed here. C swings out to the front, add a 200. So the only real difference was that negative k is that negative k. But again, if you're not sure about that kind of stuff, show your work, and definitely show your work if it's a free response question, because you always want to let the reader know you know what you're doing. So if the yam is at 20 degrees, when it's put in the oven, what is that saying to you? That at time 0 it's 20? So if at time 0 it's 20, I'm saying 20 is CE to the negative K at time 0. What is that going to happen here? So again, this is saying at time 0, the temperature is 20. I'm plugging that in. All that cancels. I subtract the 200. C is negative 180. So now I'm here. H equals CE to the negative KT plus 200. Okay, so that would be the solution to the differential equation. The best I can possibly do at this point, because I didn't have any extra information.
You write in the negative 180 for C.
Oh, yes. Hey, struggling. Thanks. Now what? I'm done with A. What now?
Plug in for the value they gave you.
Okay, so it says find your K value now, using the fact that after 30 minutes, the temperature of the yam is 120. So now I'm telling you at time 30, the temperature is now dropped to 120. So one more time, I'm bored with all this, same thing over and over again, but hopefully we'll be beaten into submission, right? So at this point, again, they're not interested in all the math it takes to get there. So I'm just gonna, they wanna see the setup to know that you've done it. And then they just pull out your calculator. 120 minus that 200 gives me negative 80. Divided by a negative 180 gives you 0.444 repeating. Natural log both sides gives you negative 0.8109, yada, yada, yada. Divide by a negative 30. And that gives you the 0.027, right? Remember, you're dividing by the negative and the 30. That gives you a 0.0270-ish. So it says find the K value. You did that. So if you really wanted the final equation, which they did not ask for, you would just take that K value, plug it back up in here, and leave the T. So this would be your final equation. If they asked for it, negative that K value, 0.027 T plus the 200. But in this case, that's all they asked. And remember, we're rounding to 3 decimals, but we never use those rounded values. Maybe as an answer, but if I have to find something else, like if I want to know, hey, what's the temperature after 6 hours or whatever, make sure you use this original value. This exact value, every value you found, make sure they're exact. And they're in your calculator. You just got to go back up and grab them and bring them back in. If you have trouble with that, talk to me. How are you feeling? How much time do I got?
8 minutes.
8 minutes.
60 now.
So you got 2 homework problems? Is that it? 90, 74, 92? What did I give you? Just one?
You have to like Stuart There's a backside to that page.
And then the next page.
Yeah, we have,
Those are optional.
we have 2 of them are required, we have 1974, 704.
Oh, yeah. Okay. Well, We'll do one. Which one do you want to do?
Whichever one's the hardest.
1970. It's going back. All right, I was in first grade. Lived in Germany. That's all I remember. Miss Brazelman. That's a Pole.
You lived in Germany in first grade.
Yeah, my dad was in the military, so I lived there for kindergarten, first and second grade.
I lived there in first grade too.
Oh yeah? You lived in Berlin? Oh yeah. When I was there, there was East and West Berlin still. So I actually went. I went behind the Iron Curtain once. Yeah. There's a train route, and when the Iron Curtain went up, the train route, they didn't redo the train because of mountains and stuff like that. So you actually, even though you might have been in West Germany, you actually went into East Germany. And I remember my brother and I were like, we were 7 and 8. We were like, what if we fall out of the train? My dad was like, you're gone, dude. There's no way we can get you back.
You mean the
We were like,
wall?
yeah,
Okay.
yeah, back when the wall before it came down and the Reagan and Gorbachev or whatever. But yeah, that was back in the crazy days. I lived in Stuttgart, but we traveled around a little bit. But I was too little to really enjoy it. Okay, 74. We got a couple minutes. It says the rate of change in the number of bacteria. So I'm just going to let, since I'm reading through this and I don't really see them making me use certain variables, I'm just going to say let y equal the number of bacteria. So this is not the question. The rate of change in the number of bacteria in Apcalc is proportional to the number of bacteria present. So that's basically saying the rate of change is proportional to the amount. Well, that's y equals c to the kt, right? Well, save yourself the trouble right here. So if I have y equals ce to the kt, it says in a certain lab experiment, a culture had that many bacteria initially. So what is that telling me? At time 0, y is 10,000, correct? And then it says 20,000 bacteria at time t1. So at some time, I had 20,000 bacteria and 100,000 bacteria at time t plus 1, t plus 10. So at t, I'm going to call that T1, and this is at T1 plus 10. This kind of problem is doubtful, but this is 1974, before we had calculators and all that kind of junk, and they were constantly trying to screw with you with algebra. Okay, so right here, I know I can at least get my C value pretty easily, right? So how am I going to do that? Plug 0 in there, 10,000 here. This is not Newton's law of cooling, so the C is 10,000. So for part A, I can jump straight to y equals 10,000. E to the kt. Now, what does it look like's happening next? If you're really creative, this is not a big deal.
We're kind of getting a new initial time.
Well, if you just stick to what you know, what's going to happen? If you stick to what you know, you're like, well, I've got 20,000, but I don't know exactly. I just know it took T1, whatever that time is. And then you're like, oh, if I have 100,000, starting with 10,000, that takes T1 plus 10. What does it seem like I would have to do to solve this? A system of equations, which is kind of nasty, and you're probably never going to see that on this AB test. But wait a minute. What am I really trying to find here? K? Didn't I give you a shortcut for K? Didn't I tell you that K was the natural log of something over the number of days or years, whatever it took to do that? What happened here that I know with confidence? It grew from 20,000 to 100,000, so it grew by a factor of 5. In how long?
10.
10 minutes. Bam. So if you can do that, you can find your K value really quickly and skip over that algebra. And that's where that little formula is really, really helpful. Now, I normally use it for like half-life, right? If I know that the half-life is 10 years. But if you really look at this, you're like, wait, it took me an extra 10 minutes to increase this by a factor of 5. Natural log of 5, 10 minutes. Punch that in my calculator, I have my K value. And once you have your K value, this problem becomes easy. And it really beats the crap out of doing the system, doesn't it?
Yup.
I think. Right, if you had to, I guess you could solve for one variable, plug it back in here, but